Okay, it's 8 o'clock. Good morning, everybody. Okay, let's see. Does anybody have any questions before we get started? Okay. Yeah. Okay. I was working this problem yesterday and the answer didn't come out quite right. And I figured out why. I forgot that. Okay. That was a cosine squared there. Okay. Not just plain old cosine. And once you put cosine squared instead of cosine of theta, so cosine of theta all squared, it comes out just fine. So anyway, that was what was wrong with it. That was yesterday. Okay, so today, oops, no, I still want this. And my notes think that I put it in September 80. Okay, it's not true. Okay, so today we're going to talk about the intermediate value theorem and the extreme value theorem, abbreviated IVT and EVT for short. The intermediate value theorem says that if you have a function that's continuous on a closed interval, AB, and f of A is not equal to f of B, and C is a number between f of A and f of B, then there must be some number little c in the open interval AB such that f of little c is C. Basically, this is because the graph of a continuous function can't be a broken line, right? You can draw the curve without raising your pencil off the page. So that this theorem makes sense in light of that. Did somebody try to come in? Okay, let me go back. No, I guess not. Yes, okay. All right, there. Okay. So, and then the extreme value theorem says that, again, if you have a continuous function defined on a closed interval AB, then f has got to reach a highest point in that interval and a lowest point. And we'll talk more about this shortly. But let's do an example. Did somebody else come in? Okay.
Yes, it's me, Britton.
Okay, so you're
I was able to make it. Yeah, I was able to make it.
Okay.
Just so for anyone else who needs this information,
okay, Mr. Rodriguez.
Use lu.net to get into the Wi-Fi.
Okay, I didn't hear that. You kind of faded out.
Sorry, I said use lu.net when getting into the Wi-Fi.
Oh, I don't know. Okay. Okay. Let's use the intermediate value theorem to show that there is a root of the equation 4x cubed minus 6x squared plus 3x minus 2 equal to 0 between 1 and 2. Okay, well, all I've got to do, a root means an x such that when you put that number x in, you get 0, right? So let's call let f of x be this function, 4x cubed minus 6x squared plus 3x minus 2. If I put 1 into f, I get 4 minus 6 plus 3 minus 2. That's minus 2 plus 1 is minus 1, which is less than 0. If I put 2 in, I get 4 times 8 minus 6 times 4 plus 3 times 2 minus 2 is 32 minus 24 plus 6 minus 2. And okay, that's 8 and that's 4. But really all I care about is the fact that that's positive. And what does that say? Well, okay, we'll figure out what the number is. This is 8 plus 4 is 12. Okay, so picture f of 1 is minus 1. That point's on the curve. F of 2 is plus 12. Okay, so I'll call that plus 12 right there. And I didn't allow enough room. But the intermediate value theorem says that in order to get from this point to that point, I have to cross all the, oh, stop it, all the levels in between. So it's got to do something like that. Okay, now it could go up and it could do lots of other things. But in particular, it can't get from below the x-axis to above the x-axis without passing through the x-axis. So by the intermediate value theorem, there is some number c in the interval from 1 to 2 such that f of c is equal to 0, okay, which would be, what was the function? 4x cubed minus 6x squared. 4c cubed minus 6c squared plus 3c minus 2. Notice I didn't find this number. I didn't find it. I just know that it exists by the intermediate value theorem. Questions? Okay, I'll take that as a no. Here's another example. Show that equation cosine x equal to x has a solution. Okay. Well, this is actually two functions. Cosine of x is one of them. I will color it blue. And it's doing something like this. Okay. And then f of x equal to x, that's another function. It's a diagonal line, in fact. Well, the diagonal line and the cosine graph intersect, right? There is a solution. And graphically, you can see it. I think there's probably only one solution, but it's right there, all right, for some number x. how would I use the intermediate value theorem to show this? Well, okay, that's the way it's written. It's two functions, but I can turn it into one. Let g of x equal to the cosine of x minus x. And since the cosine function is continuous and y equal to x is continuous, so is the difference of those two functions. This function is continuous on all the reals. But of course, the intermediate value theorem applies to closed intervals. So how about this? If I look at g of 0, g of 0 is cosine of 0 minus 0, which would be 1 minus 0 is 1, which is positive. And then I look at g of pi over 2. That would be the cosine of pi over 2 minus pi over 2. Cosine of pi over 2 is 0. This is minus pi over 2, and that's less than 0. Okay, in fact, so I looked at what happens there and what happens there. Well, then the intermediate value theorem says that there is some number c in the interval 0 to pi over 2 such that g of x, a g of c, such that g of c is 0, which is the same thing as saying that the cosine of c is equal to c. Okay. So again, the intermediate value theorem would guarantee that you've got a solution to that equation. Any questions? Notice I did have to turn this one into something equal to 0 before I could use the intermediate value theorem on it. Okay, well, what about the extreme value theorem? Let's go to that. And I suppose I should give some terms first. Okay, so the extreme value theorem says that if you have a function, a continuous function defined on a closed interval, then the function attains a maximum value and a minimum value. We're going to be talking a lot about maximum and minimum things. So how about a definition? The function f has an absolute maximum or global maximum, sometimes it's called, if at c, okay, at the number c, if f of x is less than or equal to f of c for each x in the domain of f. Okay, so in other words, f of c is the If you draw the graph, f of c is the highest level you reach. And of course, you can also define absolute minimum similarly. F has an absolute minimum min. Okay. Not mim. Minimum at C if f of c is less than or equal to f of x for each x in the domain of f. Okay. And when I was talking about, so highest point, lowest point. Back to the statement of the extreme value theorem, I said a maximum value. I'm just going to leave it that way. But okay, this is actually talking about an absolute maximum and an absolute minimum on the interval AB. So I'm reducing the domain basically of the function to the closed interval AB. And there's another term that we're going to be interested in, local minimum and local maximum, or sometimes called relative minimum and okay, I don't really need to get in that today. Okay. So why am I not? And also, all right, so the absolute maximum and absolute minimum extreme values. They're called extreme values of F. So we're going to use or apply the extreme value theorem to find where given functions defined on closed intervals have their absolute maximum and absolute minimum. Oh yeah, okay. So I got to talk about something called critical number. And Fermat's theorem. But that means I've got to talk about a local minimum and a local maximum. Okay, so okay, I do need to talk about that today. So we have this idea, okay, absolute minimum and absolute maximum, highest and lowest point. Closely related idea is a local minimum. F has a local maximum or local maximum at the number A. And this is also called relative maximum sometimes. At the number A, if for some open interval containing A, f of x is less than or equal to f of a, and I guess I should give my interval a name, I, f of x is less than or equal to f of a for each x in that open interval. And likewise, you can find the local minimum. F has a local minimum at A if for some open interval I containing A, f of x is greater than or equal to f of A for each x in I. Okay, so these are pretty straightforward ideas. Let's just draw a picture. Suppose f looks like this. Okay. Then, well, there's a, okay. Then this is it's going off to minus infinity as x goes to plus or minus infinity here. But this function, it has a highest point, right? It has a highest point right here. So that would be your absolute max. It looks like f of 0 in the picture. F of 0 is your absolute maximum. This, okay, well, this is not a closed interval. This is fine on all the reals. It looks like this function does not have an absolute minimum. There is no lowest point. But it has, let's see, it has a local minimum right there. Call that number C. At C, f of C is a local minimum. And also, it looks like at some number D, you have a local maximum. And well, f of 0 is also a local maximum. But f of 0 is the highest point. It's also an absolute maximum. Any questions? Oh, when I'm not recording. Let me go back. So I guess is it recording now? Okay, yes. All right. So sorry. But y'all please remind me if you think about it. Okay. Can you see my screen?
Yes, ma'am.
Okay, good. Okay, so I guess everything I said before, it's gone forever. But of course, I'll post the notes. All right, so we're going to be interested in finding these maximum and minimum points, okay? And the extreme value theorem says that if you have a continuous function defined on a closed interval, F's got one on that closed interval, a maximum and a minimum, guaranteed. But how do you go about finding them? Well, one of the things we're going to use is something called Fermat's theorem, one of Fermat's theorems. And the extreme value theorem, for it to hold, you do not have to have a differentiable function. For Fermat's theorem, you do need a differentiable function. And it says that if the function f has a local minimum or local maximum at the number c, and f prime of c exists, so you do have a derivative there, then f prime of c is equal to 0. So this gives us, the converse of this does not hold, by the way. If f prime of c is equal to 0, you're not guaranteed that you've got a local maximum or local minimum at that number c. But this does give us a way to start looking for possible minima and maxima. And I'm going to make another definition. We're going to look for places where f prime is 0 or f prime doesn't exist. So a critical number of a function f is a number c in the domain of f. So f is c's defined. Such that f prime of c is 0 or f prime of c does not exist. So the function has to be defined at c, but the derivative doesn't have to be. Okay. So we're going to use this idea quite a bit. If we want to find the absolute maximum and absolute minimum of a function on a closed interval, we're going to need to find the critical numbers in that interval, because those are possible places where the maximum and minimum can occur. So we'll do one in just a minute here. But let's just, first of all, let's do a problem. Oops. do a problem where we just find the critical numbers. Okay. Let's see. Let me find a nice example. How about just a cubic polynomial? Of x cubed plus 3x squared minus 24x. Okay, so I want to find all the numbers such that either the derivative is 0 or the derivative does not exist. Well, the derivative is going to exist for, this is a cubic polynomial. It's going to exist for all x. In fact, f prime of x is 3x squared plus 6x minus 24, and f prime of x exists for all x. So the only critical numbers we're going to get is by setting f prime of x equal to 0. Oh, somebody in the waiting room. Okay. Okay, so f prime of x equal to 0 would be 3x squared plus 6x minus 24. All right, well, that's a quadratic equation. Well, I can first of all, I can factor out of 3. And then I can factor. I'm going to solve this equation. So let's see, that would be x plus 4 times x minus 2. Does that work? That would give me my minus 8. Plus 4 minus 2 gives me plus 2x. Yes, that works. Okay. So we're going to take our derivative and set it equal to 0. So now we're using the derivative to give us some information about the function. And now, if you want to set your derivative equal to 0, you're probably going to want to simplify your derivative. And in this case, that means write it as a product if you can. Because if I've got two things, a product of two things equal to 0, that means that either x plus 4 is 0 or x minus 2 is 0. Okay. A times B is 0 means A is 0 or B is 0. Now, this doesn't work for other numbers. A times B is 1 doesn't mean that A is 1 or B is 1. 0 is kind of important here. Well, that says that, okay, that says that x is minus 4, x is 2. Okay, those are the critical numbers. For this function. Any questions? Let's do one more. This situation where an f prime of c does not exist, that does come up. And let me give you an example. Sorry. Looking at my notes here. All right. Probably make some of you dizzy when I go through too fast my pages. Let's look at this function. G of t. Okay, so this is another problem. Find the critical numbers of G of t equal to 5 t to the 2/3 plus t to the 5/3. Okay. Okay. This function, cube roots are defined for all real numbers. So actually the domain of this function is all the reals. Square roots and fourth roots, and they're not defined for all the reals, but cube roots and odd roots are defined for all the real numbers. Okay, so I want my critical numbers. That means I want all the places where G prime is either 0 or G prime doesn't exist. So let's take G prime. That would be 5 times 2/3 t to the 2/3 minus 1 plus 5/3 t to the 5/3 minus 1. And that's equal to 10/3 t to the minus 1/3 plus 5/3. 5/3 minus 1 is 2/3. Okay, so we get that function. Now, this function does not have domain all the reals. G prime of 0 is not defined. Because that t to the minus 1/3, that's part of G, that's really 1 over t to the 1/3. So you'd be trying to take 1 over 0. Okay. So 0 is a critical number for this function. That's one critical number. We also have, well, that's the only place G prime is not defined. We also need to check for where G prime of t is 0. Okay, and that would be okay. How am I going to figure that out? Well, what I'm going to do is to factor out, or you could think about it this way. How about I think about it as finding a common denominator. Okay, so first of all, it's 10/3, and that's really 1 over t to the 1/3. Okay, so 3t to the 1/3, my common denominator. And okay, so the 10's already over 3t to the 1/3. The 5/3 t to the 2/3, well, the 1/3's already in there. So I still need that 5. And also, this would be t to the 2/3 times t to the 1/3. Got my common denominator. Okay, so this is 10 plus 5t over 3t to the 1/3. Finding where g prime is 0 is hard if you leave that derivative in that form. It's not so hard when you have it written in that form. Okay, because now 10 plus 5t over 3t to the 1/3 equals to 0 means that the numerator is 0. But the denominator is not. And that does happen in one place. That happens when t is -2. Okay. You put -2 in for t, you get 0 with 10 plus 5t. But the cube root of -2 is perfectly well defined and not 0. So this part's not 0. Okay, so t minus 2 is a critical number. And that means that for this function, there are 2 critical numbers. Up, or not add. 0 and -2. Questions? Okay. Well, let's see. I haven't used the extreme value theorem yet or applied it. Let's do that. Let's see. Here's a good problem. Find. Okay, so we talked about critical numbers. Now we're going to find the absolute minimum and absolute maximum of f of x equal to 3x squared minus 12x plus 5 on the interval 0 to 3. Okay, so I'm going to use the extreme value theorem. I've got a continuous function is defined on a closed interval. Extreme value theorem says that I've got to have an absolute maximum and an absolute minimum. The extreme value theorem doesn't say anything about how to find them, though. Okay. But what we're going to do is to use this these ideas. Okay, so I'm going to make a list. Of critical numbers in the interval 0 to 3. It doesn't count if you get a critical number and it's not in this particular interval. It does not count. We're looking for the maximum on this interval. And also I'm going to include the endpoints of the interval. So if you want to check for the absolute maximum and absolute minimum, it can occur at one of the endpoints. So they must be checked. And then I'm gonna after I make this list, I'm gonna compute the F values. Each X in the list. And then the highest number that I get, F of X, the highest number for those F of those X's, that's my maximum, and the lowest number is my minimum. Okay. And the lowest F of X is the absolute minimum. And the extreme value theorem says these must exist. So, okay. So we have our function. Uh, 3x squared minus 12x plus 5. And we have our interval. So let's take f prime and set it equal to 0. Well, I want all the critical numbers. Okay. This is a polynomial. F prime exists for all x. So I'm not going to get any from f prime if c does not exist, that condition. They're all going to come out of where f prime of x is equal to 0. And that says that x is 2. So I have a critical number at 2. Just 1, 2, and 2 is in this interval. So my list then is going to have the endpoints 0 and 3, and then in between any critical numbers. Okay. And 2 is the only critical number. Okay, so we just have 3 possibilities here. And then, okay, so what's f of 0? F of 0, and this is, don't put it in the derivative, put it in the original function. F of 0 is 5, okay. F of 2 would be 3 times 4 minus 12 times 2 plus 5. 12 minus 24 is minus 12 plus 5 is minus 7. And when you put in 3, that's the other endpoint, you get 3 times 9 minus 36. 3 times 12 plus 5. So that's 27 minus 36, which is minus 9. minus 9 plus 5 is minus 4. Check my arithmetic. I think that's
I
right.
believe that's correct.
Okay, thank you. Okay, so what's the biggest number? Biggest number is 5 in that list. 5 is the absolute maximum. What's the smallest number? That's what happens at 2. Minus 7 is the absolute minimum. Okay, so that's all you've got to do. And what does that say? It also gives you some information on what this function looks like on this interval. F of 0 is 5. F of 2 is minus 7. I'll call that minus 7. And that's 2. F of 3 is minus 4, so that comes back up some. So the function must do something like that. But actually, we're gonna get into a lot of detail on how to sketch curves using some of this information, but right now we're just finding absolute minimum and maxima for continuous functions on closed intervals. And I'm almost out of time, so this is a good stopping place. Are there any questions? Okay, well, if not, you can go. Class is over.
Have a good day.
You too.